Okay. Hi, welcome. So we are starting a new section of material. So we are going to move to the Laplace transform method. So we're moving from being able to analyze circuits that just have two elements, RC, RL. So now we can move to things that have like 5 capacitors or 5 inductors. And you do a 5th order solution. Sounds scary? Yeah. It's actually not. And I'll show you how to do it. And it's going to be something you can feasibly do. So I would like to encourage each of you to look through. Sorry, I'm clicking on the wrong screen. I'm like, that's not opening. So on this learning materials, there's only like really 3 sections. So the biggest thing that you're going to have to learn is some new math techniques or review some older math techniques if you haven't seen it in a while. So we're going to go over a little bit more math this time. But I want you to go back and watch this introduction to Laplace transforms. It's only like under 10 minutes. If you view it on double time, it's even quicker. So just go through that. Will give you a little bit better brief introduction to what we're doing. And then the properties of Laplace transforms, go through that. Really understand like what the steps are being taken to do that. The next thing that, or the kind of the first math that we're going to tackle is this partial fraction expansion. So this technique is going to allow us to be able to use tables that are already created for Laplace. And so to be able to organize the equations into that way, though, you have to understand this partial fraction expansion. So I give you 2 methods of how to do that. And then you can choose which method you kind of like. I just don't want to spend all the time in here because some of you, it may be reviewed, others are in just different places. So do go watch it. Make sure you do understand kind of where that's coming from. All right. Any questions? Oh, and upcoming assignments. So this Thursday is going to be the Unit 1 feedback for this last unit that we did. So that will be due Thursday. And then there'll be a discussion due this Thursday. Yes.
Will we be able to use code on the next test?
Like pre-made code, you mean?
Yeah.
Yeah. Yep. So if you want to program several of your CEs in here and love programming, you're welcome to make some snippets of code that you can use, whatever language you like. Just again, just include that in your work that you submit, just in case you have an error in your code. At least you could kind of have that evaluated for partial credits. But yes, you're welcome to use some coding to do that. So the other thing we may be working with is polar coordinates. So again, if you have something that does that for you, MATLAB is fine. Just something that your calculator, if your calculator does them automatically, changes those coordinates for you. Just make sure you understand whichever tool you're using, that you use it the right way. Otherwise, it's not a very good tool for you. So that's the only thing I request, is that you make sure you're understanding how to use the tool that you choose to use. All right, so we are with lecture 5. We're here. Okay. I'll turn off for a minute. Okay. So this is our previously solve circuit the way we did it before. This is an RL circuit. It's hopefully you see that it is in series. And trying to pull up my notes. Found that it was critically damped because they're equal, solved for VC 0, VC infinity, and IC 0. So a little side note is that there is a way that you can just use these same equations and actually get the end equation instead of doing the derivative. So I kind of skipped this last time because I was like, there is a simpler way than taking the full derivative each time. So this is the technique I like to use. And so with this, you can actually just go ahead and map these for, sorry, just make sure I do write this down correctly. 2024. Okay, lecture 5. Unit 2, lecture 5. Okay. So you just map directly VC of 0 goes to IL of 0. VC of infinity goes to IL of infinity. And then IC of 0 goes to VC of 0. So this VC, the difference is that this VC of 0 is found a little different. So that one you have to use from the equation that you derive. So VC of 0, if you see there, you're going to put 0 in for t. What will VC of 0 be? What's e raised to the 0? Okay, good. So e raised to the 0 is 1. Oh, no, that didn't work, did it? That becomes 0, sorry. Okay, I'm just going to go down here. VC of 0. Wait a minute. Why is VC of 0 1.6? Let's see. I'm a little lost for a second. They end up being the same equations for IL of t. And I'm going to have to come back to that because I, for some reason, can't see why VC of 0 is put as 1.6. So I'll have to come back to that one. All right. So we're going to move to, like I said, having these more complicated circuits. With every time-dependent element that you have, you're going to have an order of magnitude to the end equation. So if we have 5 elements in there, 3 capacitors, 2 inductors, it's going to be a 5th order equation. So not fun to do with just loops. So what we're going to use is this Laplace transform technique. And the thing about the Laplace that we have not been able to see is that before we had for an input, we would use a switch and it would be a DC source that it would switch on or off. So a very simple input. What we can now look at with Laplace is a really complicated input that can be described mathematically in any way. That mathematical equation can be transformed by Laplace into a signal, a mathematical description, and we can use that to solve the circuit. So what this technique is that we use the transform to go into this new domain of S domain. So from the S domain, all of our differential equations then the time domain become algebraic in the S domain. They simply add, they simply subtract, they divide. Very much simpler than an integration and a differentiation. So that's why this technique is like, oh, I can do this. I can add and subtract in my head if I want. So these are much easier techniques. You get a solution, and then you use the inverse Laplace transform to go back to the time domain. So this is what we're going to do, is change that element from a time domain element and actually model it as a S domain element. So we transform the circuit to S domain. We then apply the KVL, KCL, node voltage, solve for an unknown variable, and then transform back to the time domain. So that's all we're going to do. Sounds really easy, right? I'm hearing you like, yeah, it will be easy after you learn a few math techniques. Okay, so with this, we first need to know, like, how do we change over these two elements that are time domain? So with the time domain, where did these go? Okay. So if you remember, we have, copy these. Okay, so the Laplace, let me back up to the Laplace. So this is the Laplace transform. It's a capital F, and then we're in the S domain, so we use S. So F of S is equal to the L, the squirrely L is meaning a Laplace of a time domain signal F of t. And that is actually this integration from 0 minus to infinity of ft e to the minus st dt. That's all that the Laplace means. The inverse Laplace is this one, where you have the squiggly L with the -1. So that denotes a inverse Laplace. And then it's of that capital F of S, and then that goes back to F of t. And then you take 1/2 pi j and integrate from sigma minus j infinity to sigma plus j infinity, the F of S, which is your S domain signal, ESTDS. I am not going to make you do these integrations. So we look at tables. So Laplace transform pairs. Let somebody else do that. Let the computer do that. So this is what we're going to use. So it will do your integration for you. Just use the pairs. So you know that delta t, do you guys know what delta t is? Called the impulse function. So if I have, this was always confusing to me too. So all it means is that I have at a specific time, t, if there's a 1 out in front of it, this will be a 1. If there's a 5, then this is a value of 5. And it's just right at that specific time, that value is there. So that's all that the impulse means, is that at that specific time. This could actually be a constant voltage, 5 volts. But if I'm measuring it right at t, I call it an impulse function. And so I say delta t, this would be 5 delta t, meaning that just right at that certain time of t. That translates over to a Laplace is 1. So in the Laplace domain, that's going to just be a function of 1. Each of these Laplace pairs, this is what the video goes through, is actually that mathematical derivation of the most common ones, is that the delta t minus t is just a shift and OU of t. So this is 1. Oh, did not pull it up on this one. Let's see. Okay, so these step functions are the U of t. So these are described in chapter 5 of your book. So all this is that at time 0, after time 0, there is a signal there. So these are kind of like what the switch does. So you can model a switch in a simulation by using this U of t function. So all it means is that after time 0, I have a value. Before time 0, I do not. So V naught would be some amplitude of it. So this would be, 5 U of t would look like this. So this would be 5 U of t. You can have a shift of ut minus 3 means that at a positive 3, so the t minus 3 just shifts it. So that at 3 minus 3 would be 0, then I have the step function going up. So these are called step functions. The most common ones are usually because we deal with real time. They're going to be U of t or U of t minus 3, or just a shift in time of what you want to be 0. Most of the time it's just U of t because you're like, I can define when my U of t starts. So that would be at 0. So those are going to be the most common ones. But instead of writing for t greater than or equal to 0 or for t greater than or equal to 3, all you have to do is write U of t or U of t minus 3. Does that make sense on how to write these? Okay. You can also, well, I'll get to that after we look at a signal. All right, so this 1 or U of t is just 1 over s, and so on. So each of these is just a transform pair. So when I see this signal, so if I have a battery, 5 U of t, and there's a switch going on, meaning I just have a start at some point, 5 U of t would translate into what in the Laplace domain? Five over s. So the U of t is the 1 over s. So if I have some number in front, it's just 5 over s. So those go to the properties of Laplace. So if I have a constant k, it just multiplies also in the Laplace domain. If I add two functions, I add the two functions in the Laplace domain. If I multiply the time of it, then it's this one. If I have shifts, then in the time domain, I have an e raised to the minus ts. If I have an exponential in the time domain, that translates to a s shift in the s domain. So these are the most common ones that you're going to see. There's also the derivatives. But for the most part, you're not going to see those here. But you'll get into those in the future. So just be aware of the properties of the Laplace transform. Kind of note these, and then the Laplace transform pairs. So the next thing we need to know is, like, how do we actually change the elements themselves? So to change the elements, well, actually, I'm going to go back to some of those properties. So the derivative property, I'm going to use to actually change the elements. Because we have that property of the derivative and then the integration one we need. All right, so we're going to use these to actually make the elements, and then we can just use those each time going forward. Okay, so we have this equation, VL, L, DL, DI, I can't talk, but DIL, DT. So with that, we have that VL, I'll write it over here. Okay, so VL is equal to L, DIL, DT. And so I have a derivative which transforms in the S domain to the S f of S. So if I take the L over here, right, I have 1 over L VT VL, and then I can do the partial of dt, and then I have the integration, and these are over everything. And so this side ends up equaling IL going from infinity to minus infinity, but ours really just starts at 0. So we call it, 0 minus. So I can do 1 over L, 0 minus VL dt, and then add on the IL 0 minus. And this would be IL at infinity. And then I can change this to be, oh, this didn't describe it very well. I can multiply it by L again. Oh, this didn't work very well. Let me try this a different way. All right. So differentiating this, do it again. VL, okay, going to S domain, becomes a big VL of S. And then it's L, and then DIL dt is going to be S, and then the I of S minus the initial value, but it's times by L, so IL of 0 minus. So this is just using, I think that's an easier way to look at this property. I'm going to erase this one. That one didn't make as much sense. So all this did was just take it was started out as VL is L di dt. So I just took L times the FS minus F0 minus. So that looks like this one. And so SL is going to be the value of that inductor, and IL is going through it, and then a minus, so that's why the minus is on the top, IL 0 minus. And so that looks like a battery. And then my element here looks like a resistor. So all I'm doing is using a voltage source, and the element of the inductor now changes to look like a resistor with value SL. So that is just from changing it over from the time domain to the S domain. And I have IR, which R is the value of SL times IL. And then the battery value is just IL 0 minus. So same thing can be done with the IL. This is an integration. And so the integration gives me this form. So depending on what I'm trying to find with these elements, I can use either one. Same thing with the capacitor. I start out with the equation, and that changes into an element that can be treated like a resistor with value 1 over CS, and then the initial value over S. And then in this case, it's a plus, so I have the positive on the top. Yes.
The 1 over, well, so when we change the inductor to a resistor, does it have a unit attached? Like, is it an ohm?
It's ohms. Mm-hmm. Yep. So that SL will be in ohms when we change into the S domain. So now we can do is just use these models, literally replace them with the other elements. So looking at this, find a different one. Okay, we did it. Okay, there we go. So here's our circuit, and we can replace the capacitor. And literally, you just put that over the other one. And connect. And then for the inductor, the same thing. And so with that, then we just solve the circuit. We treat so now our Vs of t is going to be with the switch. We just do Vs of t, U of t. And so this is going to be closed, and we do Vs of t, U of t. We change to the S domain. So that becomes a, whatever signal is the V, S, and then the U of t is over S. And then we treat the R and the capacitor and the inductor as resistances, and then all of the other voltage sources. So to find I here, I'm going to take a loop. So I'm going to use plus. This will be minus. Going down will be minus. This will be a minus, minus, and then a plus. So this will be plus Vs over S minus kind of my IS. R is 4, and then a minus IS of 1 over SC minus VC0 minus over S minus I of S, SL, and then a plus L, IL 0 minus. So that is my loop, and now I can solve this for I of S.
Do you know what S is?
So no, it's a variable. Okay. So Vs will be a known value. That's the battery value. So that would be some constant, 5 volts, 10 volts. So it would be 10 over S. Vc of 0 minus is going to be found based on this circuit. So we can go back to find that. So it was open first and then closed. So it's 0 minus. So this is open. This will be open and this will be a short. So VC will be 0 and IL of 0 minus will also be, will be what? Will be 0, correct. So VC of 0 minus of 0 minus is 0. So in this case, this one will go to 0 and this one will go to 0. So we would just be left with IS, VS over S, and this on the bottom. All right, so let me give an example. Let V of S, or let V naught, let me just say V of S equal to 1.6 U of T. So VS of S is just going to be 1.6 over S. U of T is that step function. It just means for time greater than 0. It's that value. So 1.6 will look like this. So this is 1.6 U of T. Yes.
What kinds of circuits would we want to use this Laplace transformation instead of the over Dan under Dan stuff that we previously learned for RLC circuits?
So complicated input. So instead of just a simple battery. Or if you have more than one, more than just the two elements. And even for those two, like I'm showing you, you can use it here. Right. So if you like this technique better, you could just use this one instead. You still have to do like circuits at like 0 minus, 0 plus. Yeah, so here you have to find that 0 minus for VC and IL. And then depending on which elements you're using, you're going to have to use those. So I did the ones in series because I like in this circuit, it was very easy to use a series instead of adding in a complicated parallel in there. Some situations, a parallel might be better. And again, you'll have to just find that IL 0 minus and the VC 0 minus. Okay, so going back to this, this is actually, okay, I'm going to rewrite that one. So this will be 1.6 over S. And then I can multiply this out. Let's see, C is 0.1 farad. And L is 0.4 Henry. So this ends up being 1.6. I can bring the S to the bottom and then multiply it by all of this on the bottom. 4S plus 1 over 0.1s plus 0.4s. And then bringing the s in, I get uh, 4s plus 1 over 0.1. Was that 10? Just write 10. Plus 0.4 squared. And then I need to manipulate this so that I can find the roots of it. And so from here, I would then bring the, like divide everything by 0.4 so that I have just an s squared in the first one. So divide everything by 0.4, that gives me, bringing out the 0.4, then this is 4 over 0.4. Actually, I'm going to write the s first. So s squared, and then 4 over 0.4 s, and then 10 over 0.4. And so you can see that this is the same equation. If I bring out 0.4, it becomes 0.4s squared. I have to divide the 10 by 0.4 if I bring it out, and then I have to divide the 4 by 0.4. So 1.6 divided by 0.4 becomes 4. And then this is s squared plus 10s plus 25. Do you guys remember how to find the roots of this? Okay. So remembering back to roots. So a quadratic, let's see, ax squared plus bx plus c equals 0 gives you x is equal to minus b plus or minus square root of b squared minus 4ac over 2a. So in this case, to do the partial fraction expansion, you always want to have a 1 for the s squared. Otherwise, it doesn't work out correctly. So always put a 1 here and then solve for the s. So here s will equal to be minus 10 plus or minus 10 squared minus 4, 1 times 25 over 2. Is that 0? Right, 100 minus 100. So is that just negative 5? No. Is it just plus 5? Why is that not working out right? Minus b plus minus b. Should be plus 5. I don't know. I don't know. Things are not working out to me this morning. 25. Oh, it will be minus 5. Okay, there we go. So s equals minus 5, which means that s plus 5 is the root. So s plus 5, s plus 5. Okay, so the roots of this is s plus 5 times s plus 5. So partial fraction expansion is where once I have it in this form, another page. So this is really written as s plus 5 squared. And it is, I guess I can tell you, it's always going to be like a over the root. This is considered multiple roots. And so for multiple roots, you have to do the one that's the highest root until you get to 0. So you have a squared, then you have a 1. And so it's going to be of the form a over s plus 5 squared plus b over s plus 5. Yes.
Multiply with 4 in here for partial fractions is 4 going is equal to 4. You said it. Oh, thank you.
Yep. So these are equal to each other. So 4 over s plus 5 squared is equal to a over s plus 5 squared. Do we already have? Okay. I'm just going to, we don't even have to do partial fraction expansion because we have this one. So the table, so looking at the transform back to the time domain, once we have it in the form of a number over S, so I'm going to go backwards because this doesn't, we don't even need to see this one. I'll get to partial fraction expansions in a minute. So once we get it to a form that matches the table, so in this case, the s plus a squared matches this one. So we have 4 over s plus 5 squared. And so this is our I of s. And so we want to now go to the time domain from this. So what does that look like using this transform? So we have 4. The table doesn't have 4 in there. So what happens to the 4? It's multiplied out. So we just use that constant out. So that's going to be 4. And then if we bring the 4 out, then it's 1 over s plus 5 squared. In this case, our a will be 5. And so we can just write this as te to the minus 5t u of t. And this is our IL of t equation. And that is exactly the same as what we had using the technique we used up there. So 2 different ways of solving the problem now. Oh, is there a question? No, just raising. Okay.
Do we still need to find out whether something is over there?
Nope. Now you can graph this and see what that form looks like.
Wow. So those compare.
Yeah, so you can't like look at this and just say, but looking at that equation, you'd be like, oh, over time, you'd be able to say that's critically damped. Yeah. But looking at the graph, you might see it or you might not. So, all right, questions about this technique. So what did we do? Let me go backwards. What did we do first? Thanks, Carson. Yes, I saw that later. Uh-huh. Okay, so changed it to the model of the S domain model for the elements. Then what?
So the IS times 4, for example, is IS just like is that from one of the tables? Like, how do we get IS? Does that just mean the current times the 4 ohms, or is that?
So I just use the variable I here, and that's changing that I variable that I want to solve for into the S domain.
We have to I because it's in the S domain. So.
Yep. That was the only reason why I changed it to that capital I.
Okay, so that would translate to the current through that 4 ohms.
Mm-hmm.
Okay, cool.
And through the inductor and through the capacitor. So it's IL in other words. I could label it IL if I wanted. Okay, so change the elements into the time domain. So literally redrew them with that initial value with VC of 0 minus over S or LIL 0 minus. From there, what did I do? So I did a voltage loop, in this case, one loop. Parallel, I'm probably going to have to take node voltage. And I got this nice equation that ended up having a very easy root to find. And I could have looked at that and said it was S plus 5, but I didn't see it. So use the quadratic. From there, I look at the table to see which pairs would match it. So if I have a squared, I can use that number 6. A lot of times you're going to see 3, where it's just 1 over S plus a number, plus, some other number over S plus a number. And so whichever form I have in the S domain, I just can use that right back to the time domain. I have to just identify what the variables are. So in this case, I would have to identify what that A was, and then look at where it goes in the time domain. So for the one that was S plus A squared, we had A was 5. And so that's where it came to TE to the minus 5T over, or times U of T. All right, so solved it and then moved back to the time domain. All right, so let's look at this one. How would I write this more complicated input signal? Any ideas? Okay, so I'm going to use a step function, but it's not able to be described just by one step function. So I'm going to use 2 step functions. And they're both at 6 amps. So if I create, how would I describe the first one? So right at t equals 0, it goes up to 6. So what would this one be? Okay, so this would be 6u of t. Now we'll be at 6 amps. So how do I get rid of, I want it 1, another color. I want to kind of remove all that, right? Correct. Okay, so this form would be 6u of t minus 1, right at 1. And if I subtract those, I would end up with that form. So this would be my input signal. So I'll call this this is IS. So IS is equal to 6ut minus 6ut minus 1. All right, so now I have a mathematical form of this signal. Did you have a question? Yeah.
If it was a delta, if we're using the delta, would it just be like a spike? What does that look like?
Yeah. So literally it is like if you're looking at a screen and all of a sudden you see a spike go up, and it is used usually to describe that spike in a change. So yeah, and usually it's a high value, like 100 delta T, or, because you have like a spike in current or a spike in voltage. And so that would be what it is. If you're looking at trying to change this at a specific time, you'll use that to describe a battery at one specific time. But usually it's easier to be like, well, I'll say that my time at 0, so then I use like 5-volt battery U of t. So either way, if you're trying to trigger an event, a lot of times you'll use that delta to be like, at this one particular time, I want to have that value go. So that would be another time you would use like a delta t to model it. But realistically, it is just a spike in a voltage or current. That answer your question? Okay. Other questions? Yes.
Yeah, I'll ask you later. I don't know how to phrase this properly.
Okay. So I want you guys to break up into small groups. I want you to redraw this circuit with the model of the S domain for the elements and change this signal into the S domain. And then we'll chat. Okay.
So sorry for missing.
Oh, boy.
Cool. I'm glad it worked out. So I'm looking at the 6 UFT, right? And that shows the amplitude of the 6 amps, right? T0. Do we not have to show that it comes back down to 0 in the second part?
Backed off the 6 minus or 6 UT minus 0.
The subtraction sign is showing that. Okay.
That will be 0 after that.
Okay. So it's the subtraction. So like if this went higher, would that be a plus?
Yeah.
Okay.
Then you would add on
okay.
Another.
Thank you. That makes total sense.
Yeah.
IS in the S domain goes to IS over
So it depends on what your function is. So 6 U of t goes to 1 over S. And then you have to look at the one with the time shift.
That makes sense. Okay.
So the UT minus T is going to go to E minus TS over S.
Okay.
And then say you have like a sinusoid. So you had an actual sinusoid signal, it would go to omega over S squared plus omega squared.
Yeah, I remember. Yeah. Yeah. That's essentially.
You model like the inductance or the capacitance in the S domain similar to resistance. Is that like why you can S times IL is equal to the voltage, like a voltage source when you do the transformation?
So what do you mean?
I'm saying that like does like the inductance kind of become our resistance basically, and that's why it becomes a voltage source when you multiply it times the resistance.
So this is just so this is going to be treated like the resistor because then it's like I times R, and then that R value is SL. This one you model like a voltage source because with the value, just because you can't really do an I times R again. And it doesn't look like a current source because you're doing, you know, as far as the voltage across it will be VL.
Okay.
So you want to do voltage drops. So that's why it's a voltage source. And this is accounting for that initial value.
Okay.
If you have it.
So is this kind of similar to like a voltage loop?
Okay. Yeah. So the voltage loop would be V. Oops. So plus VL minus ISL IL plus. Brought up here. So if I was to kind of do a loop, this goes up, and then this is a plus to minus because of the direction of the arrow would be on the bottom. So this would be minus plus. So this is plus VL minus SLIL plus LIL. 0 minus equals 0. And then you can rearrange that to be VL equals SLIL minus LIL. 0 minus.
Okay, thank you.
Does that make sense?
Yeah.
So it is a voltage loop across that one. This form is a current summation.
Oh,
So
okay.
VL over SL. And then this one is VL, the current is already defined there.
Oh, okay.
And so it's the same thing. You're just doing a current summation for that one.
Oh, okay. Thank you
That
so
make
much.
sense?
Yeah.
Are those tables in the unit 2? Try it again.
Go further.
Oh, go back. Which one did you press?
Unit 2.
They're in the book. You have the book handy. They're in chapter 7.
Is the book?
Well, you can do multiple, right? That should take it.
So I think go to the syllabus might be the easiest thing.
Supposed to have a physical copy, but something with the U and the DA stuff's not going through, so painful.
And then click on that one, and then scroll down. I think it's on the bottom one, just right there, and then free download. And then just fill that out, and then they give you a link, and you can download it.
Is there like another space where the tables are on the campus?
On the lectures. So the lecture semester handouts and lectures, there'll be one on there too, under lecture 5.
Oh, right. Thank you.
So there's one there too.
Question. What are we trying to model? Are we trying to model it? Yeah, but like, are we trying to model the current across the inductor or the capacitor? Or...
I didn't specify. Let me see what I saw for. Find IC of T.
IC of T.
Oh. Okay. Yep. Okay, so the goal of this is to find IC of T. Where did mine? Sorry. I just had a question from another person who was asking where the tables were. So they are in your book or in the notes. So you can download the book if you don't have the book. I suggest downloading that book. On this, you're trying to find IC of T. So you are going to redraw this with, I would suggest the ones that are in parallel, so that everything is kind of in parallel, and then do a node voltage to solve for that one. So the first thing, or one of the other things we need to do is change this IS to the S domain. What will this look like? 6 over S, correct? So it should look like that in the S domain. Did everybody get that? If you didn't have a question about that one. Okay, so let me go back up to the tables. Okay, so the U of T is 1 over S. If you have a number, remember you can kind of bring that out. Let me go down and rewrite it here. So if you have a number, I can rewrite that number. I can write this as 6 times 1 over S minus e to the minus, or sorry, backwards. This one I can write as 6 times u of t minus u of t minus 1. So I can bring the 6 out in front, and then u of t was 1 over s. Whoever asked me that, do you guys all see that 1 over s from the ut? Okay. Then I also have a minus here. So I just leave the minus there. And then ut of minus 1 translates to e to the minus 1s over s. So then I can just rewrite that one. Whoever asked me to explain that, did that make more sense? Okay. So you just look at the table, identify the variables for your equation. If there's a constant, it is still a constant in the S domain. So you just leave it. If there's a minus 1 out in front, just leave the minus 1 out in front. If it's a 6, leave the 6 out in front. So I can write it either way that it's written here, 6s over 6s minus 6e minus s over s, or 6 multiplied by those. Okay, I'm going to like the form of the parallels. So I'm going to take these for the capacitor. And for the inductor, I can redraw it or copy and paste in my case.
Does the capacitor one go over the inductor one?
What do you mean go over?
So you're currently redrawing, so to speak, and I noticed that the one that has the inductor is replaced over the one that's a capacitor.
Oh, did I place them wrong?
Maybe I'm just asking.
Yep, I replaced them opposite. Yeah, okay. No, they should be in the other places.
Okay.
Sorry.
It wouldn't matter.
No, because they're in parallel, it wouldn't matter. But this would not be IL going through there, and this would not be IC going through this one. Cool. So yes, I should be doing those there. So IC is going to go through this one, and IL will go through this one. So depending on what I want to find, I can do either, you know, I can find IL if I want, I can find I1 if I want, just depending on whatever I want to find. I like to do node voltage, as you guys know, so I would do node voltage here. Before I do node voltage, I'm just going to call that Vx. It's probably easier to find IL of 0 minus and VC of 0 minus. Now, what is 0 minus in this case when I don't have a switch going on? I look at the input signal and see right before time 0 what's happening there. And then I'm going to use that value and solve for the other variables. So in this case, at 0 minus, our input is 0. So what happens with the inductor and capacitor? I heard somebody say it. VC0 will be what? 0. And IL of 0 minus will be. So you can basically ignore those elements because they're going to be 0. So they'll open up. And now when I write my node voltage equation, I'm going to have minus IS of the S, Vx over R, Vx over Ls, and Vx over 1 over Cs.
Sorry, I just missed it. What did you say about when there's no switch when we get 0 minus?
You're going to look at the input signal and see what happens right before 0.
Okay.
And in this case, it was 0 before 0, so that input is 0. Otherwise, you look at what that value does to the circuit. All right, so IC is going to be Vx over 1 over CS, which I could write that as Vx times CS. So once I find Vx, I can find my IC. So combining all the like terms, 1 over R, 1 over LS, and I can write this as either CS or 1 over CS. And so this gives me Vx is IS over this. And so IC is IS. I can write my IS. CS all over this. Okay, to simplify this, if I want to get rid of, like I'm trying to get it into where I just have the roots on the bottom so that I can match it up with the table easier. So to do that, I have 1 over LS on the bottom, so I'm going to try and get rid of that S. So that's where I would start by multiplying the top and the bottom by S. So that gives me CS squared on the top. And then this will be S over R, 1 over L, CS squared. And then if I bring out the C, they'll cancel. So I can bring a C out from the bottom and the top, and they can cancel. So if I do that, then that means that this term down here has to be, I should add that in here. This has to be divided by C, divided by C. So this becomes S over RC. This is a 1. That was a 1. I just miswrote it. Or wait, did I miss an S? No, 1 over LC. There we go. 1 over LC. And then S squared. So that gets it into the form of the S squared that I want. And then this will become 6 over S minus 6e to the minus S over S squared divided by this. And then from there, I would need to know the values, and then I can do partial fraction expansion and match it up with the table and move back to the time domain. So the next step is partial fraction expansion to make this simpler to then identify what it matches with in the table. All right, questions about the steps that are needed for these and about redrawing them? Yes.
Can you remind me what we're solving for IC this time and not IS?
IS was our input and it was given.
And we wanted IC.
And we wanted IC, or I told you that to find IC.
Oh, because it's told us to find IC.
Yeah.
Okay.
But I was saying you could find IL, I1, whatever you want to find there. Or just Vx, you could write the equation for Vx and translate it back to the time domain too.
Okay.
So now instead of being stuck, before it was like, oh, I can only really find the IL or the VC, and then I have to integrate it or differentiate it. Now it's much easier also to find all the other variables in there.
Oh,
much easier too. Because you find it in the S domain and just move it back to the time domain. All right, making sense? Is this very overwhelming? Okay. First homework next week is just going to be partial fraction expansion. So we'll work on that next time, and we'll move more to the math steps, and then we'll come back to this technique of actually solving the full circuit. Okay. All right, so watch those videos, kind of feel more comfortable with the material itself. Yes. Oh, yes, somebody was saying that was locked. I apologize. If somebody has this pulled up on their computer, will you just see if you can now access module 2? Make sure it did get published. All right, see you guys. Anybody online able to check that? Make sure module 2 is now working.
Give me 1 moment.
It's working now? Okay, great. Somebody verified it out in class. Thanks. Have a great day, guys. See ya.